In this lecture, we'll look at 4 architecture approaches for machine learning systems. Here are the 4 we'll be looking at. Now don't worry if you're not sure about what they all mean yet, I'll be going over each one in detail. First, a word on model serving formats. When you train and export a machine learning model, you need a way to persist the model. Now different file formats exist for doing this. First of all, you can serialize the model object with the Python pickle module. This is what we'll be doing in this course. There are also certain open source tools like MLflow, which provide a common serialization format for exporting models from different machine learning frameworks. And there are also language agnostic exchange formats to share your models, and a few of them are listed here on the slide. It's good to be aware of these options, as there are some notable risks and drawbacks to the simpler pickle format. Like when you mix 32-bit and 64-bit machines or Python versions, you can get some different results when you deserialize your pickled model. There are also security vulnerabilities to be aware of, so I'll link to some of those details in the lecture notes. The first architecture we'll look at is the embedded approach. In this scenario, we embed the trained model as a dependency of our application. So in short, we either install the model in our application, for example via pip install my model, or we pull the trained model into the application at build time from some file storage like AWS S3. The application is then able to make predictions on the fly by calling this pre-trained model that it has access to, and it does this within some process that it controls, hence the on-the-fly moniker. An example of this would be if we had a single Django application which does our house price predictions. So our Django app would serve HTML pages. On one of those pages we'd have a form where a user would enter certain information, they'd submit that form, and then the Django application would take those inputs, produce a prediction for the house price, and return that prediction back to the client, so the user's browser. Variations on this architecture include mobile apps, which make use of native machine learning libraries, for example Core ML on iOS, and they do this to perform predictions as part of the application's process again, so on device. In all of these cases with this design, we're trading off simplicity against flexibility. The applications are simpler, but if you want to make a model update, then you've got to redeploy your entire application, and in the case of a mobile device, you've got to release a new version of your app. The second machine learning system architecture we'll look at is the dedicated model API. In this architecture, our trained model becomes a dependency of a separate machine learning API service. So to extend our Django house price prediction application example that we talked about on the previous slide, when a form is submitted to the Django application server, that server would make a second call to a dedicated machine learning microservice, and that microservice would be exclusively responsible for returning the predicted house price. Our Django app might make this call via REST or gRPC or via some kind of message broker like RabbitMQ. With this architecture, we reverse the trade-off of the first architecture we looked at. So we have the increased complexity of maintaining another separate service, but we now have flexibility because we're able to keep our model deployments separate from our main application deployments. We can also scale our main server or our model microservice separately so that we can deal with high traffic or potentially serve other applications. A third machine learning system architecture leverages streaming platforms like Apache Kafka or Apache Pulsar. In this scenario, we have a training process which publishes our trained model to the streaming platform, and our application consumes the model at runtime, not at build time, so it then is able to subscribe for any model updates. Now here again, we make the simplicity-flexibility trade-off, because maintaining the infrastructure, so this kind of streaming platform, requires far more engineering sophistication and maturity, but it does allow for models to be updated without any applications being redeployed, because we can ingest a model at runtime. In our Django application example, the application would now be able to consume from a dedicated Kafka topic where new versions of our house price prediction model would be published. This means that when a new version was made available through Kafka, our Django app could consume that at runtime. There would be no need to redeploy the application, so we could seamlessly upgrade a model. A fourth architecture design is the only asynchronous prediction design we will explore. In this scenario, predictions are triggered and run asynchronously, perhaps by our application, or alternatively on a scheduled job. After a few hours or even days, the predictions would be collected in a database or some form of storage, and the application serves the predictions via a dashboard or a report or any potential UI. This is a more outdated architecture, but it's also much more forgiving. We can inspect the predictions before allowing customers to see them. We might have a flag in the database saying that predictions are validated or checked. And so long as we store the original requests, we can rerun predictions if we find mistakes. Here we're making the trade-off of increased flexibility and less chance of making mistakes for the inability to offer predictions on the fly. Now, to be clear, there's no such thing as a best architecture. There is simply the set of trade-offs which best meets your system's requirements against your time constraints. The table on this slide summarizes some of the trade-offs, and in this course we'll be building out an application which adheres to architecture pattern 1 and which we can easily adapt to architecture pattern 2. Some of you will be wondering where the trained model we've referred to in these diagrams comes from, and in the next lecture we'll look at the components and pipelines necessary to create these trained models within the architectures 1 and 2 that we've just looked at, and adhering to some of the best practice principles that we've been talking about in this section. Alright, I'll see you in the next lecture.